Hi guys, so you've survived to part 1 and part 2 of our second week GIS 305 lectures. I know there's a lot of stuff in here and they're long lectures. Part 3 will be more of the same. Do feel free to listen in to these at an accelerated pace if that helps. Um, let's go to our lecture by now and talk about how remote sensing images work. So sensing the image. What do we mean by that? Well, we've talked about sensors aboard platforms, in our case, satellites in most cases. We've talked about the energy source of our passive sensors being sunlight, and we've talked about how it interacts with the atmosphere, the Earth's surface. Now we will talk a little bit about more about how these sensors work and how they collect data for eventually our end application. So remote sensing images, what are they? Well, they consist of one or more bands. We'll talk about what bands mean. And these bands contain measurements of reflected irradiance. Now you should know what that means by now. In specific ranges of the electromagnetic spectrum in gridded or raster structures. So we will talk about what bands are and how the measurements are made. And delivered in gridded or raster structures. So a raster is more or less a black and white image. So we're now pretty familiar with digital imagery where data is delivered in rows and columns that define pixels or cells. And each cell is associated to a given value. In remote sensing, we call these digital numbers. So these values are the digital numbers of each pixel, and they're typically associated with an increase in brightness of the electromagnetic signal that is recorded. So that's a raster structure, or sometimes called a grid. Now, how can satellite imagery deliver images that can be displayed in color? So how can different objects have different colors in remote sensing imagery? That's a very important concept. It's kind of complicated. Hopefully we'll get to this in an understandable way. Now, first of all, they have to be displayed on your screen. Every color you're looking at on your screen needs to be displayed in some kind of way. And the way that is done, if you were to zoom in with a strong magnifying glass, and I've tried it, it works, what you would see on your screen are these little color elements that are associated with each pixel. So each pixel is actually the repetition of 3 underlying little signals. One is blue, one is red, and one is green. And if you were to zoom in more, this is what it would look like. Obviously, if a pixel contains only only red light, it will be apparent as red to your eye. But if a pixel, like in this case, were to display red and green, actually our eye will send the signal to our brain that what we are looking at is yellow. And if the pixel is small enough, then its resolution cannot be resolved by our visual cells at the back of our eye, and we will mix these colors together and determine that this is actually yellow. And depending on the level of brightness of the signal, if it's very intense or more dull like this, we will then see it as a bright color or a dark color. So that's how screens typically work and display colors. So for remote sensing data to interact with screens in ways that we can interpret them as colors, a certain number of things need to happen. So here, this is basic color theory. If you add different color signals, so if you're actually shining different kinds of light on a surface. If you mix these kinds of light, if you have pure green and pure red mixed together, you'll see yellow. If you have pure blue and red, you'll see magenta, and so forth. And the mix of green, red, and blue, because these are the three primary colors that our eyes are sensitive to, if you mix them equally, you'll obtain white. So these are the primary colors of red, green, and blue, and that's why we often talk about RGB screens and RGB imagery, and this is also called the RGB color space. Now, know that in opposition to this, if you have, oh, let me come back, if you have subtractive colors, and I'm assuming I have, oh, here it's on this slide, let's just discuss it here. For some reason it's not displaying on my PowerPoint. Subtractive colors are when you mix ink, and because ink absorbs colors and does not emit color, you have to take the reverse strategy here, where your yellow ink absorbs, basically what it means is that ink absorbs blue light and it re-emits everything else, so that everything else is a mix of green and red, so it looks yellow. Similarly, the magenta ink is an ink that absorbs green light, so that it reflects back everything that is in the red and blue, and to us it looks magenta, and so forth. So that's why we say cyan, magenta, yellow, and the K stands for the level of black that is used in printing. So back to our presentation, and hopefully it won't be too glitchy. So the way RGB signal is displayed on screen is that it's any kind of mix of red, green, and blue. And depending on the level of intensity of the red, green, and blue signal, and here you'll have an example of R, G, and B, depending on the level of intensity, and in this case it ranges between 0 and 255, then you'll have some kind of a variation in hue, but also in brightness and saturation. So the hue is the actual mix of color. The brightness is the level of, of brightness. So is it dark or is it very bright? And the saturation will also be a factor in determining which color you will have as a result of this mix of red, green, and blue. And because in this case our screens are capable of 256 different levels for each of these color elements, we have typical screens with 16 million different color combinations that are possible for our eyes to appreciate. Now, why that is relevant in remote sensing is because, especially to view remote sensing data in true colors, we need to replicate this RGB, red, green, and blue mix of the light signal. So that's why, for instance, this Landsat image here, these squares refer to these squares here. So the Landsat platform and the ETM Plus sensor here are designed to record electromagnetic signal, the reflectance, in different parts of the electromagnetic spectrum. Here you've got the band number 1. So literally the sensor here is collecting image that is specific to one part of the electromagnetic spectrum. And you'll note that we're in the blue area here. So this in Landsat imagery will be the area in which the sensor records a signal for blue light. You'll have the same thing done for green light, and that's band number 2. and red light in band number 3. And then once you're past that, you're in the near infrared area. Then you've got shortwave infrared and thermal infrared imagery, for which Landsat also delivers um, images. So these are all separate images, and that's very important to know. They're all displayed typically in black and white because they record a level of intensity of the signal for each portion of the electromagnetic spectrum that the sensor is sensitive to. So that's for Landsat imagery. Now let's just read through this paragraph because these are very important concepts to understand. So Earth observation sensors that capture data in multiple bands produce what are called multispectral images. So it's actually an image of the same target that is split into the different portions of the electromagnetic spectrum based on the sensor's capability to distinguish between these elements. So most commercial satellites such as Landsat, Spot, Rapid Eye, WorldView 2, 3, and 4 today generate multispectral images covering the visible and infrared portions of the electromagnetic spectrum. So again, here is our electromagnetic spectrum. You've got very short wave radiation here that is like gamma rays and X-rays. Then you've got UV radiation that has slightly longer wavelengths. Then you have wavelengths in that portion of the spectrum to which our eyes are sensitive. But you also have longer wavelengths that we will call infrared because they're lower energy levels than red light. Then you'll have microwave radiation. Radio waves are the actual radio waves that we use for communication, and long radio waves. So that's your electromagnetic spectrum here. And high energy light is at this end of the spectrum, and low energy light is at this end. And that little portion of the electromagnetic spectrum that is expanded here is the portion in which typical remote sensing sensors are designed to work. Now, there's also here imaging systems that capture data from numerous and commonly narrow bands over a wide portion of the electromagnetic spectrum, and they produce what we call hyperspectral images. So you've got an example here. These bands, denoted by these narrow blue stripes, are all separate bands, so separate images that are captured by the Hyperion satellite sensor. And there's literally hundreds of these over this portion of the electromagnetic spectrum, and that's a totally different kind of image. And that is called hyperspectral images. We won't be using hyperspectral images as part of this course, but do know that they exist and they're very important in a certain number of applications and research. So multispectral sensors typically provide less than 15 bands, while hyperspectral sensors can provide more than 100 spectral bands, and that's why they're called hyperspectral. Now you've got another example here of a satellite platform, the Aster satellite, where again these boxes on the diagram indicate the portions of the electromagnetic spectrum to which its sensor is sensitive and can produce different imagery. You'll note that there's a much greater number of them here and here, so it's a more advanced sensor than the Landsat ETM Plus sensor. But do note also that, interestingly, this satellite does not provide any data for the blue portion of the spectrum, so it's actually impossible to view this satellite imagery in true colors. And the reason why that was designed is because the scattering we talked about just affects this portion of the light spectrum so much that it kind of renders it useless for anything else than really just typically viewing the images I shouldn't say that. There's actually a bunch of applications that still are very useful for using the blue portion of the spectrum, but that's often why satellites will ignore the blue portion of the visible light spectrum. Okay, um, it will be important, I think, for you to understand everything that is shown here in this diagram. I'm thinking of using it again, possibly in the exam. Note that you have the atmospheric transmission percentage here. So the atmospheric transmission windows that we talked about. Here you have areas in which the atmosphere just absorbs so much energy that we don't even bother designing sensors for this kind of light. You've got those, so these are absorption windows and these are transmission windows. Be aware that visible and near infrared light is where most of our remote sensing applications focus, and this includes also thermal infrared for certain bands of certain remote sensing sensors. Okay, lots of material here, but hopefully this is understood. I will point out another number that we haven't talked about here, but we will touch on later. This 30M denotes 30 meters, and what this means is that the pixel on the ground for a Landsat ETM Plus image, the pixel on the ground is 30 meters by 30 meters in size. It is the same for the Hyperion data. However, it varies for the Aster data from 15 in these high energy wavelengths to 30. The reason why it decreases is simply because there's less energy to detect, so your pixel needs to be bigger, and that also applies to these thermal infrared pixels where these are quite a bit bigger, and because they're subdivided they need to be made even bigger compared to the Landsat thermal infrared bands, in which the pixels are delivered in sizes of 60 meters by 60 meters. Very important slide. Okay, so we're looking at a multispectral image. Here the pixels on the ground I think are 15 meters in size. I believe this image was acquired with a sensor that is mounted on a plane. Anyway, that doesn't matter. This is an image from your textbook, but just note how this is imagery that was taken at the exact same instant, but just with a sensitivity to different parts of the electromagnetic spectrum. And you have them here, band 1, band 2, band 3, and so forth. Interestingly, D here, so the near infrared signal in image D, note how different it is from everything else, and note how certain targets will sometimes have very high reflectance in certain wavelengths and low reflectance in other wavelengths. This is going to define the spectral signature of different surfaces, and that is one of the most fundamental notions that you'll need to understand to work with remote sensing data. So now to display multiple bands on screen, essentially, if you have signal in that part of the electromagnetic spectrum that our eyes perceive as being blue light, you will assign that signal to the blue part of your RGB screen. If you do the same with the green and the red, then on screen what you will be looking at is an image that is very close to true colors in the real world. Now I'm noticing now that there's an image that my PowerPoint won't display, and that was this image. Let's just look at it together. When we're displaying on screen in red, green, and blue, the reason why screens are designed that way is because our eye is also sensitive through these cone cells to these 3 wavelengths of energy. And depending on the level of excitement of our cells, we get a different nervous signal sent to our brain. And if it's mostly these red cells that are excited, then our brain knows that we're looking at something that is reflecting red wavelengths. And inversely, if the three are mixed together, then we perceive it to be white. And here our rod cells are an indication of how bright the light is. So this is kind of an information on the intensity of the light and not so much its wavelength. So that's just a bit of anatomy of your eye there for you. So if we go back to this slide, so this is how you display true colors if your satellite captures signal in the red, green, and blue portion of the electromagnetic spectrum. But you can also play with this and display what we call color composites. So if you use Landsat Thematic Mapper, the sensor here as an example, you can take the blue, green, and red bands, these three first ones. Let's ignore 4, 5, 6, and 7 for now. But if you use only these three and you assign the red to red, the green to green, and the blue to blue, that's where you get natural color viewing. But you could also play around with this. You could assign, actually, let's consider near infrared here, band 4 to red, band 3, which is typically red, but assign it to green, and the green assign it to blue, and you obtain, for the same image, the same target, you obtain a different viewing option. And this is the standard false color composite. It's very useful to characterize the vegetation cover of a given area. But you can also do a number of combinations and play around with viewing options using any one of these bands in different display setups. So those are color composites. So this is a bit of a review graph, but let's go over it because we're going to include interesting information. So if we consider passive sensors versus active sensors and the wavelengths in which they operate, we will note that none of them actually operate in the, well, no, I shouldn't say that. You can use spectrometers that focus on gamma rays, but that's not at all something we'll be touching on in our case. Like we said earlier, we're going to focus on the visible and optical domain that is defined by visible light and near infrared light. So you'll have these multispectral scanners. Photography typically operates in this area, but you also have thermal scanners that focus on more longer wavelengths of our optical domain. Then you have passive microwave sensors or radiometers. Radiometers are simply instruments that measure electromagnetic radiation. But in active sensors, the laser scanners, so LiDAR, typically work in green, red, and mostly near infrared wavelengths. And you have radar and imaging radar that works in much longer wavelength in the microwave domain. Okay. Another notion that is important, we've talked about swath, and that's the size of the image footprint on the ground, or the width of the footprint. And note how there's a compromise between the size of the image that is typically recorded by a satellite sensor and the spatial resolution. The spatial resolution is the size of the pixel on the ground. So if you want high spatial resolution imagery, this is an old graph, so there's many more sensors today that we could add to this graph, but the trend is still the same. A satellite such as the IKONOS satellite here will offer high spatial resolution, so small pixels on the ground, but its swath will be quite limited. I think in the Iconos example, I think we're talking about 11 kilometers across. At the other end of the spectrum, we've talked about Landsat 7 imagery and how its spatial resolution is much more coarse. At this point in time, we'll say it's medium resolution in 2019. So its resolution on the ground is around 30 meters. Well, it is delivered in 30 meter by 30 meter pixels, but its swath is much greater. It's 185 kilometers across. So know that there is this element of compromise, which is an important factor in deciding which type of image is most appropriate for your application. And finally, I'm just going to throw this image up here on our slide because it's an image that I'm thinking, again, that you should be sure to understand every element of, because it will likely be a good image to do some assessment of your understanding on. So study this image for an eventual quiz or exam, please. Okay, a little bit more review. Multispectral images are images where the image data is captured within specific wavelength ranges across the electromagnetic spectrum, and this records information as different wavelength bands. So we talked about red, green, blue, near infrared, medium infrared. That's kind of the typical structure of a multispectral image as compared to, oh, and this is, an example of multispectral image band 1, 2, 3. You have here an example with 7 bands. And if you compare this to hyperspectral imagery, here we're talking about data that is captured within much narrower bands of the order of 10 to 20 nanometers, so very narrow band of the electromagnetic spectrum. And it consists typically of hundreds or even thousands of bands. So if, for instance, you have a target for which you have all these finely detailed, narrowly defined bands of information that your sensor is sensitive to, then you can recreate a curve where you have, for each little narrow bit of this wavelength spectrum, you have a signal of reflectance. And if you put all these data points one behind the other, you're going to define a curve, right? And this is often very diagnostic for things like given minerals. It's a highly diagnostic tool, and this is often used in remote sensing. We won't be doing any kind of mineral detection applications, but you do need to know that this reflectance curve is what we call a spectral signature. So that's the footprint here of kaolinite, but it also applies to a number of other surfaces, and that's what we'll be talking about next. So a spectral signature is that curve of reflectance that you obtain if you are able to detect the level of reflectance for each narrow portion of the electromagnetic spectrum. So if you have here, consider the example for healthy vegetation, you'll note that healthy vegetation has a peak of reflectance in this area here around 0.5 micrometers or 500 nanometers. And that is green. And that's why, if you know that this portion of the spectrum is the portion for which our eyes are sensitive, that's why our eyes perceive vegetation or chlorophyllc vegetation as being green, because the signal that it reflects back is mostly in this part of the electromagnetic spectrum. So that's the curve, and note how suddenly, boom, there is this huge increase in reflectance, and that is due to spongy mesophyll, and this is basically energy that is not, it's not high enough level of energy for the plant to use, so it just wants to get rid of it, otherwise it's just going to heat up and dry. So plants have evolved chemically to reject and reflect away the energy that is received in the near infrared portion of the electromagnetic spectrum. But then there's also the water content of the vegetation that absorbs certain portions of the electromagnetic spectrum, the light that hits the leaves of vegetation. So this is an example and a classic example of a spectral signature. I will now um, bring to your attention a graph that I've seen in many um, instances, but that actually seems to me like it's erroneous, so incorrect, and that is the following graph. So this is actually pulled from a presentation, a webinar that is published and distributed by NASA. And you will recognize here the spectral reflectance curve of healthy vegetation. And there's other spectral curves that are given for soil and water. But added to this graph are the Landsat bands, the portions of the electromagnetic spectrum in which the Landsat bands are defined. And note how even NASA forgets to tell us if this is Landsat TM, which is the 5th Landsat satellite, or is it Landsat ETM Plus, which is Landsat 7, or Landsat 8? We don't know. I will say here, however, that it is Landsat 7, I will assume, or 5 or 7, because they're quite similar. Anyway, I'm going to say that this is a problematic graph because if you were to consider, and I'll move here, consider the curve and the bands, you would say that the signal here in the first band, which is blue and green and red, suggests that this vegetation would actually look and appear to our eyes as being mostly red. And this is typically not what vegetation looked like. So I'm going to say that someone drew this graph and through these bands, actually the bands are where they're supposed to be because they're in the correct portion of the electromagnetic spectrum, but I'm going to say that this line was not drawn correctly on this graph and that it's a problem. So be conscious of that kind of issue with graphs like this. But I've seen this one in many instances. A more correct example of a real spectral signature is something like this. So note that I will backtrack one slide here. This curve, you can only get to this curve and display it as data if you have data for every little narrow portion of the electromagnetic spectrum, right? When in reality, if you're using a Landsat image, you will have only one value for each band. So you will only have 7 values along this curve. And that's why a typical Landsat-based spectral signature will look a lot more like this, where you have 1, 2, 3, 4, 5, 6 in this case. Not sure why the 7th isn't there. We could probably determine it with the wavelength. They've ignored one of the bands. But in this case, what you're looking at is a much more typical spectral signature, and this is what we will be working with as part of our assignments. So these are the kind of data sets that will be used in typical remote sensing applications to distinguish between different surfaces, because each surface has a given curve. And note how in this case they've given us these confidence intervals around these values that define how variable the signal can be given the kind of surface we're talking about. Another example here where classification schemes for a given image have shown that different surfaces have different spectral signatures. The most distinctive in this case is likely this bushy vegetation where you have a very high value for near infrared emission or reflectance. This is a normalized reflectance, so be conscious of um, this being a different axis than some other graphs have shown. But anyway, um, this is just an illustration of a spectral signature for you to consider and the differences that we can observe between different surfaces. And again, consider the fact that a given surface will have varying levels of reflectance in any given band, which sometimes makes it confusing to distinguish between surfaces based only on spectral signatures. Now, if you want to learn a bit more about spectral signatures, or just know that this notion of a spectral signature is very important in distinguishing between various surfaces in hyperspectral imagery in particular. Here you have, again, a mineral that you have a spectral signature for. This is kind of the standard signature that is published for this particular surface. So the USGS, and this stands for the United States Geological Survey, publishes thousands of spectral profiles that researchers can use as references for spectral signatures of given materials, in particular minerals, because they're so predictably, they react in so predictable ways with light. And I believe that's all for part 3. Move on to part 4.